Hello and welcome to this exciting 1-hour PySpark tutorial for beginners. I'm Coder2J, and today we're going to embark on an incredible journey into the world of Apache Spark, combining theory and hands-on practice to help you master the fundamentals. Whether you're a seasoned programmer or just getting started with Python, this tutorial is tailored just for you. We'll take you from zero to hero in PySpark, without any prior experience required. Throughout this tutorial, we'll be diving into both theory and practical examples based on the latest Apache Spark version 3.4.1, ensuring you understand the why and how behind each concept. And guess what? You can download all the demo source code via the GitHub repo link in the video description to follow along with the live demos. In this action-packed 1-hour session, we'll kick things off with an introduction to Spark, demystifying what makes it so powerful for big data processing. Then, we'll get our hands dirty by guiding you through Spark installation on both macOS and Windows, ensuring you're set up for success. Next, we'll explore the core components of Spark, SparkContext, and SparkSession. You'll learn their roles, differences, and how to create them using PySpark. But that's not all. We'll delve into Spark RDD Transformations and Actions, where you'll see how to manipulate data in Spark using the Resilient Distributed Dataset. And here comes the exciting part, Spark DataFrames. We'll introduce you to this powerful data structure and show you how to create Spark DataFrames from scratch. You'll witness firsthand how easy it is to work with structured data in Spark. But wait, there's more. We'll cover Spark DataFrame operations, giving you the tools to perform various transformations on your data. We'll also dive into Spark SQL, allowing you to leverage the power of SQL for data analysis within Spark. So, are you excited yet? I know I am. But here's the cherry on top, bonus video. If we hit 50,000 views, I will do a practical end-to-end video about how to build a machine learning pipeline with PySpark. If we continue hitting 100,000 views, I will create another practical end-to-end video about Spark streaming. So make sure to hit that subscribe button, ring the notification bell, smash the like button, and share this video with your fellow aspiring data engineers, analysts, and scientists. Okay, let's get it started. In today's session, we'll explore what Spark is, the problems it solves, why it's better than other alternative tools, who should learn Spark, and the prerequisites needed to learn PySpark. So what exactly is Spark? Spark is an open-source distributed computing system designed for big data processing. It provides a unified analytics engine for processing large-scale data sets and performing parallel computations. Spark addresses the challenges of working with big data by offering high-speed, in-memory processing capabilities. It efficiently handles complex data processing tasks, including data transformation, machine learning, graph processing, and real-time stream processing. Now, let's talk about the problem Spark solves. Traditional data processing systems often struggle to handle large volumes of data and perform computations in a timely manner. Spark overcomes these limitations by distributing the data across a cluster of machines and processing it in parallel. This distributed computing model allows Spark to process data much faster than traditional systems, making it ideal for big data analytics and real-time processing. So why do we need Spark when there are other alternative tools available? Spark offers several advantages that set it apart from other tools. Firstly, it provides fault tolerance and reliability by automatically recovering from failures, ensuring data integrity and job completion. Secondly, Spark's in-memory processing capability allows it to cache frequently accessed data, reducing disk I/O and significantly improving performance. This makes Spark well-suited for iterative algorithms and interactive data analysis. Thirdly, Spark's versatility allows it to seamlessly integrate with various data sources and frameworks, including Hadoop, Cassandra, and SQL databases. It also provides extensive libraries for machine learning, graph processing, and streaming analytics. And it provides APIs for multiple programming languages, including Python, Java, Scala, and R, making it accessible to a wide range of developers. Now, who should learn Spark? Spark is particularly valuable for data engineers, data scientists, and big data professionals who deal with large-scale data processing. It empowers them to efficiently process, analyze, and derive insights from massive data sets. Lastly, let's talk about the prerequisites needed to learn PySpark. While previous experience with distributed computing systems or big data concepts is beneficial, it's not mandatory. However, having a solid understanding of programming fundamentals and some knowledge of Python will be helpful when working with PySpark. That wraps up our introduction to Spark. Today, we'll guide you through the process of installing and setting up PySpark with JupyterLab on both macOS and Windows 10. Let's get started. First, we need to install the Java Development Kit, or JDK. This is essential for running PySpark. Spark runs on Java 8, 11, or 17. Here's what you need to do. Visit the Oracle website oracle.com/java/technologies/downloads and download the latest version of JDK 17 for macOS. Make sure to select the right version for your Mac. ARM version is for Mac with Apple Silicon chips, while the x64 version is for Mac with Intel chips. Once the download is complete, run the installer and follow the instructions to complete the installation. To verify the Java installation, we can simply run the command java version, and the Java version info should be returned. Step 2. Install Apache Spark. Next, we'll install Apache Spark, the framework that powers PySpark. Visit the Apache Spark downloads page at spark.apache.org/downloads.html and select the latest stable version of Spark. Choose a pre-built package for Apache Spark, specifically the one labeled pre-built for Apache Hadoop 3.3 and later. Download it and extract the package to a directory of your choice. Here we will move it to the directory /user/coder2j/apps and change the Spark folder name to Spark. Step 3. Install Python. Now, let's install Python. Spark runs on Python 3.7+. So make sure you have the latest Python version, for example, Python 3.10. If you don't know how to install Python, check out this video. Once you have it, create a Python env using the command python mvin.pysparkenv. Activate it. We can see the env name at the beginning of the prompt. Step 4. Install PySpark JupyterLab. We're almost there. Let's install PySpark, find Spark, and JupyterLab, the popular notebook interface for Python. Step 5. Launch JupyterLab and use PySpark. It's time to launch JupyterLab and start using PySpark. In Terminal, enter the following command, JupyterLab. This will launch JupyterLab in your default web browser. Here we can create a new notebook and rename it as PySpark Get Started. First, we need to set up the environment variables required for PySpark. We set the Spark_home variable to the path where Spark is installed. In this case, is /user/coder2j/apps/spark. Change it to match your extracted Spark directory. Let's set PySpark_driver_Python to Jupyter and PySpark_driver_Python_OPTS to lab to specify that Jupyter should be used as the driver for PySpark and the JupyterLab interface should be used. Finally, we specify the Python executable to be used with PySpark by setting PySpark_Python to Python. Then we import the SparkSession class from the PySpark.SQL module. The SparkSession class is the entry point for working with structured data using Spark SQL. Next, we create a SparkSession object named Spark using the builder pattern. The app name sets the name of the Spark application. Let's say PySpark Get Started. The getOrCreate method either retrieves an existing SparkSession or creates a new one if it doesn't exist. In the end, we create a simple data frame using the createDataFrame method. The data frame is created from a list of tuples data, where each tuple represents a row with 2 columns, name and age. Finally, the show method is called to display the contents of the data frame. After execution, once you see the data frame value is output, it means you've successfully installed and set up PySpark with JupyterLab on macOS. Let's get started on installing and setting up PySpark with JupyterLab on Windows 10. Step 1. Install Java Development Kit, JDK. To begin, we need to install the Java Development Kit. Don't worry, it's a straightforward process. Spark runs on Java 8, 11, or 17. Visit the Oracle website, oracle.com/java/technologies/downloads, and download the latest version of JDK 17 for Windows. Once the download is complete, run the installer and follow the instructions to complete the installation. To verify the Java installation, we can simply start the command prompt and run the command Java version, and the Java version info should be returned. Step 2. Install Apache Spark. Next, we'll install Apache Spark, the framework that powers PySpark. Visit the Apache Spark downloads page at spark.apache.org/downloads.html and select the latest stable version of Spark. Choose a pre-built package for Apache Spark, specifically the one labeled pre-built for Apache Hadoop 3.3 and later. Download it and extract the package to a directory of your choice. To extract it, you need the 7-zip application. Make sure you have it installed. Now we use the 7-zip to extract the file to the download folder and change the Spark folder name to Spark. Here we will move it to the directory C/users/coder2j/documents/apps. Step 3. Install Python. Now, let's install Python. Spark runs on Python 3.7+. So make sure you have the latest Python version, for example, Python 3.10. If you don't know how to install Python, check out this video. Once you have it, create a Python env using the command python mvin.pysparkenv. Activate it. We can see the env name at the beginning of the prompt. Step 4. Install PySpark Jupyter Lab. We're almost there. Let's install PySpark. Find Spark and Jupyter Lab, the popular notebook interface for Python. Step 5. Launch Jupyter Lab and use PySpark. It's time to launch Jupyter Lab and start using PySpark. In Terminal, enter the following command, Jupyter Lab. This will launch Jupyter Lab in your default web browser. Here we can create a new notebook and rename it as PySpark Get Started. First, we need to set up the environment variables required for PySpark. We set the Spark_home variable to the path where Spark is installed, in this case, is C/users/coder2j/documents/apps/Spark. Change it to match your extracted Spark directory. Let's set PySpark_driver_Python to Jupyter and PySpark_driver_Python_OPTS to lab to specify that Jupyter should be used as the driver for PySpark and the Jupyter Lab interface should be used. Finally, we specify the Python executable to be used with PySpark by setting PySpark_Python to Python. Then we import the SparkSession class from the PySpark.SQL module. The SparkSession class is the entry point for working with structured data using Spark SQL. Next, we create a SparkSession object named Spark using the builder pattern. The app name sets the name of the Spark application. Let's say PySpark Get Started. The get or create method either retrieves an existing SparkSession or creates a new one if it doesn't exist. In the end, we create a simple data frame using the createDataFrame method. The data frame is created from a list of tuples data, where each tuple represents a row with 2 columns, name and age. The resulting data frame is assigned to the variable df. Finally, the show method is called to display the contents of the data frame. After execution, once you see the data frame value is output, it means you successfully installed and set up PySpark with Jupyter Lab on Windows 10. Congratulations! You have successfully installed and set up PySpark on your macOS and Windows 10 machines. In this video, we are diving into the concepts of SparkContext, SparkSession, and their differences. Let's get started. Before we delve into the differences, let's understand the individual purposes of SparkContext and SparkSession. The Spark context represents the connection to a Spark cluster. It acts as the coordinator, responsible for task execution across the cluster. It was the primary entry point for Spark functionality in earlier versions, such as Spark 1.x. On the other hand, the SparkSession was introduced in Spark 2.0 as a unified entry point for interacting with Spark. It combines the functionalities of SparkContext, SQL Context, Hive Context, and Streaming Context. This versatile component supports multiple programming languages, including Scala, Java, Python, and R, and seamlessly integrates various Spark features. Now that we understand their purposes, let's explore the differences in functionality between SparkContext and SparkSession. The SparkContext provides core functionality for low-level programming and cluster interaction. With SparkContext, you can create RDDs, Resilient Distributed Datasets, perform transformations, and define actions on the data. On the other hand, the SparkSession extends the functionality of SparkContext. It introduces higher-level abstractions, such as data frames and datasets. These abstractions enable structured querying using SQL or the DataFrame API, data source APIs, machine learning algorithms, and streaming capabilities. The usage patterns also differ between SparkContext and SparkSession. In earlier versions of Spark, you would explicitly create a SparkContext object to interact with the Spark cluster. This context allowed you to create RDDs, apply transformations, and manage cluster resources. However, starting from Spark 2.0, it is recommended to create a SparkSession object instead. This unified entry point internally manages the Spark context and simplifies interaction with Spark. The SparkSession offers a higher-level API for structured data processing using data frames and datasets. Lastly, let's touch upon backward compatibility. The Spark context is still fully supported in the latest versions of Spark, such as 2.x and 3.x, for backward compatibility. You may need to use it in specific scenarios or when working with libraries or APIs that rely on it. However, the SparkSession is the recommended entry point for Spark applications since Spark 2.0. It provides a higher-level API and combines the functionalities of several contexts, making it more convenient to use and offering better integration with the latest Spark features. To sum up, SparkContext and SparkSession have different purposes and functionalities. SparkContext is low-level, while SparkSession is higher-level. SparkSession simplifies interaction and supports structured data processing. While SparkContext is still supported for backward compatibility, SparkSession is the recommended entry point for Spark applications. I hope this video clarified the distinctions and helped you understand their respective roles. In today's video, we will explore the different approaches to creating a Spark context in different versions of Apache Spark. Creating a Spark context is essential for establishing a connection to a Spark cluster and enables us to harness the power of Spark. Let's get started. In Spark version 1.x, the recommended approach to creating a Spark context is relatively straightforward. We import the Spark context class from the PySpark module and use the constructor to create a Spark context object. We provide an application name as a parameter, for example, MySparkApplication. From the Spark context, we can see that we are running the Spark application MySparkApplication in a local Spark cluster with Spark version v3.4.1. And the Spark UI is a web-based graphical interface provided by Apache Spark that offers insights into the status and performance of Spark applications. It provides information about jobs, stages, executors, SQL queries, and storage, helping users monitor and optimize their Spark jobs. Once we finish using the Spark cluster, we can call the stop function to shut down the currently active Spark context. However, in Spark version 2.x and later, the preferred entry point is the SparkSession. Let's take a look at how to create a Spark context within a SparkSession. Here, we import the SparkSession class from the PySpark.SQL module. We use the builder pattern to create a SparkSession object, providing an application name like MySparkApplication. Then, we obtain the Spark context from the SparkSession using the SparkContext attribute. Again, the Spark context contains info about the cluster version, application name, and the URL of the Spark UI. And you can shut down the currently active Spark context by calling the stop function from the Spark context or SparkSession object. That's all for creating a Spark context in different versions of Apache Spark. You've learned the recommended approach for Spark 1.x and how to create a Spark context within a SparkSession in Spark 2.x and beyond. In this video, we'll explore how to create a SparkSession in PySpark. Let's get started. Creating a SparkSession in PySpark is straightforward. We begin by importing the necessary module, in this case, the SparkSession class from the PySpark.SQL module. Next, we use the builder pattern to create an instance of SparkSession. The builder object allows us to set various configuration options for the session. Optionally, we can set an application name using the appName function. This name will be displayed in the Spark UI, providing a meaningful identifier for your Spark application. For example, my Spark application. Additionally, we can chain other configuration options using the config function. This allows you to specify the master URL, set properties, add packages, or any other relevant configuration specific to your application. For example, we can set the executor memory to 2 GB and the number of shuffle partitions to 4. Finally, we call the getOrCreate function on the builder object to obtain a SparkSession instance. If an existing SparkSession is available, it will be returned. Otherwise, a new one will be created. Once the SparkSession is created, you can use it to perform various operations. This includes reading and writing data, executing SQL queries, and leveraging the powerful DataFrame and Dataset APIs. For instance, let's check the SparkSession object itself. The Spark version, app name, and Spark UI have been printed out. Let's navigate to the Spark UI. In the Environment section, we can also see our Spark application name and the config we did for the Spark executor memory and the number of shuffle partitions. When you have finished using the SparkSession and want to release the resources, it's important to call the stop function on the SparkSession object. This gracefully shuts down the SparkSession and frees up any associated resources. Remember, stopping the SparkSession will also stop the underlying Spark context and terminate any ongoing Spark jobs or tasks. And that concludes our tutorial on creating a SparkSession in PySpark. In this video, we are diving into the concepts of Spark RDDs and RDD operations. Let's get started. RDDs, or Resilient Distributed Datasets, are the backbone of data processing in Apache Spark. They provide a distributed, fault-tolerant, and parallelizable data structure that allows us to efficiently process large datasets across a cluster of machines. Let's take a closer look at some key characteristics of RDDs. First, immutable. RDDs are immutable, which means they cannot be modified once created. Instead, transformations on RDDs create new RDDs, allowing us to apply a series of transformations to the data. Second, distributed. RDDs are distributed across multiple machines in a cluster. Spark automatically partitions the data and distributes it across the nodes, enabling parallel processing. Third, resilient. RDDs are designed to be resilient to failures. Spark keeps track of the lineage of transformations applied to an RDD, allowing it to recover lost data and continue computations in case of failures. Fourth, lazily evaluated. RDD transformations are lazily evaluated, meaning they are not executed immediately. Spark optimizes the execution plan and evaluates transformations only when necessary, such as when an action is triggered. Lastly, fault-tolerant operations. RDDs support a wide range of fault-tolerant operations. Transformations like map, filter, and reduce allow us to process and transform the data, while actions like collect, count, and save enable us to retrieve results or write data to external storage. RDDs in Apache Spark support 2 types of operations: transformations and actions. Let's explore each of them and understand their main characteristics. Transformations are operations that create a new RDD from an existing RDD by applying some computation or manipulation on the data. One key characteristic of transformations is that they are lazy, meaning they do not execute immediately. Instead, they build a lineage graph to track the applied transformations. Some common transformations include map, filter, flat map, reduce by key, sort by, and join. These transformations allow us to perform computations and manipulations on the data within RDDs. Actions, on the other hand, are operations that return a result or perform an action on the RDD, triggering the execution of all preceding transformations. Actions are eagerly evaluated, meaning they compute the result immediately and may involve data movement and computation across the cluster. Examples of actions include collect, count, first, take, save, and for each. These actions provide us with the final results or allow us to write the data to an external storage system. Now, let's dive into the demo. How to create RDDs? The first step in working with RDDs is to create a Spark session. The Spark session serves as the entry point to Spark functionality and provides a way to interact with various Spark features. To create a Spark session, we need to import the Spark session module and initialize a new Spark session object with the builder pattern. Here we give the RDD demo as the app name. With the Spark session set up, we can proceed to create RDDs. RDDs can be created from existing collections or by parallelizing an existing collection. In this example, we created an RDD called RDD by parallelizing a list of numbers. Now, let's see how to retrieve all the elements from an RDD using the collect action. The collect action returns all the elements of the RDD as a list. RDDs can be created from a variety of sources. For example, let's create another RDD from a list of tuples. Each tuple represents a record and consists of a name and an age. After performing the collect action on it, we can see that all the rows elements have been printed out. RDD Operations, Actions. RDDs support various actions that allow us to perform computations on the data. Let's explore some of these actions in more detail. The count action returns the total number of elements in the RDD. Now, let's get the number of element of the RDD using the count action. The first action returns the first element of the RDD. Now, let's retrieve the first element of the RDD using the first action. Similarly, we can use the take action to retrieve a specified number of elements from the RDD. For example, taking the 2 elements from the RDD by passing 2 as a parameter to the take action. Lastly, we have the for each action, which allows us to apply a function to each element of the RDD. For instance, we can simply print the value for each element. RDD Operations, Transformations. RDDs also support transformations, which are operations that create a new RDD from an existing one. Remember that transformations are lazy, meaning they do not execute until an action is called. Let's explore some of these transformations to gain a deeper understanding. For example, we use the map transformation to convert the names in the RDD to uppercase while keeping the ages unchanged. The resulting RDD contains tuples with uppercase names. Next, let's move on to the filter transformation. The filter transformation allows us to filter elements based on a condition. In this example, we filter the RDD to retrieve records where the age is greater than 30. We can also perform aggregations using transformations like reduce by key. The reduce by key transformation groups elements with the same key and applies a function to their values. In this case, we calculate the total age for each name. Lastly, let's sort the RDD using the sort by transformation. The sort by transformation allows us to sort the RDD based on a specified key. In this example, we sort the RDD in descending order of age. Read or write RDDs from or to text file. Spark provides the capability to save RDDs to a text file and read RDDs from a text file. Let's explore how to accomplish these tasks. The Save as Text File action saves the RDD to a text file. Each element of the RDD is converted to a string and written as a separate line in the text file. We can see the output.txt file has been saved in our project directory. Now, let's create a new RDD by reading the text file we just saved. The text file function allows us to read a text file and create an RDD from its contents. Each line of the text file becomes an element in the RDD. By using the collect action, we can retrieve all the elements of the RDD. That concludes our introduction to Spark RDDs and RDD operations in PySpark. Understanding these concepts is crucial for working with big data processing using Apache Spark. In today's video, we'll be exploring an essential concept in Spark, data frames. We'll learn what data frames are and why they have advantages over RDDs. Let's get started. Data frames are a powerful abstraction in Apache Spark that provides a higher-level API for working with distributed and structured data. In simple terms, a data frame is like a table in a relational database, where data is organized into rows and columns. Data frames offer schema information, allowing Spark to optimize the execution of queries and apply various optimizations. Now, let's explore the advantages of data frames over RDDs. First, optimized execution. Data frames provide Spark with schema information, enabling it to optimize the execution of queries and perform predicate pushdowns, leading to faster and more efficient processing. Second, ease of use. Data frames offer a high-level, SQL-like interface, making it easier for developers to interact with data compared to the more complex RDD transformations and actions. Third, integration with ecosystem. Data frames seamlessly integrate with Spark's ecosystem, including Spark SQL, mlib, and graphics, enabling users to leverage various libraries and functionalities. Fourth, built-in optimization. Data frames leverage Spark's Catalyst Optimizer, which performs advanced optimizations like predicate pushdown, constant folding, and loop unrolling. Lastly, interoperability. Data frames can be easily converted to and from other data formats, such as Pandas data frames in Python, enabling seamless integration with other data processing tools. Let's see a quick code demo comparing the usage of RDDs and data frames to read and process data. In this example, we will read a text file containing some paragraphs about the introduction of Apache Spark. Then count the number of occurrences of each word. To begin, let's set up the PySpark environment. We'll import the necessary modules and configure the environment variables. Next, we'll create a Spark session, which is the entry point for interacting with Spark functionalities. Now, let's start with RDDs. We'll read a text file, split it into words, and then count the occurrences of each word. Let's see the top 10 most frequent words and their respective counts. Moving on to data frames, we'll achieve the same word frequency analysis using a data frame approach. Finally, let's display the top 10 most frequent words and their respective counts using data frames. You can see that the data frame code is more concise and closer to SQL-like syntax. To sum it up, data frames provide a more user-friendly and optimized approach to working with structured data in Apache Spark. In today's video, we're going to dive into an essential topic, creating data frames from various data sources like CSV, JSON, and Parquet. Let's get started. In the first step, we need to set up our environment to work with Spark and create a Spark session as usual. Reading CSV files into data frame. Now, let's start by working with CSV files. CSV stands for comma-separated values, which is a common format for tabular data. We'll begin with a simple example of a single-line CSV file. We'll use a bash command to display the first 10 rows of this CSV file. This file contains information about products, such as their ID, name, category, quantity, and price. After that, we'll read this CSV file into a data frame. We define the path to the CSV file and use the spark.read.csv method to read it into a data frame, making sure to set the header option to true as the first row of our CSV file is the header. We can display the schema and first 5 rows of this data frame with the functions print schema and show. The schema helps us understand the data types of each column. We found the type of columns are all string, which is obviously not correct. Let's fix it by providing it with the explicit schema since we know what the data type of the column should be. We'll define a schema using the struct type and struct field classes from the PySpark.SQL.types module. Also, we need 3 schema types: string type, integer type, and double type. Every column type is defined by a struct field with a column name, data type, and if it is nullable. Here, the ID and quantity are integer type, Name and category are string type, and price is double type. Then, we'll read the CSV file into a data frame using this explicit schema by passing the defined schema to the spark.read.csv function parameter schema and display its schema and content. Now, the schema of the data frame is correct. What can make the schema definition easier is the infer schema. It is a convenient option that allows Spark to automatically guess the data types of columns. It can save us from manually defining schemas. What needs to do is to set the infer schema option of the spark.read.csv function to true. And boom! Spark automatically finds the correct schema for us. Reading JSON files into data frame. Moving on to JSON files, which are a popular data format for semi-structured data. It stands for JavaScript Object Notation and is used to store data in a human-readable format. We'll start with a simple example of a single-line JSON file. Let's check the first 10 rows of this JSON file using the bash command. We can see every row is a valid JSON record for single-line JSON. To read it into a data frame, we can simply use the spark.read.json method with the path of the JSON file. As always, we'll show the schema and content of the data frame. We can see the proper schema is automatically set. Reading multi-line JSON files. JSON files can also have each record with multiple lines. We'll show how to handle such multi-line JSON files. From the bash command result, we can see a JSON record is defined in multiple lines. To read it into a data frame, we need to set the multi-line option to true. Once again, we'll display the schema and content of the data frame. The schema is also correct. Reading and writing Parquet files. Finally, we'll explore Parquet files, which is a columnar storage format that's highly optimized for analytics workloads. We'll write the data frame we've been working with into a Parquet file. To achieve that, we can just call the method df.write.parquet with the output Parquet file path. Let's refresh the data folder. We can see the data frame has been saved as a Parquet file. Now, reading this Parquet file back into a data frame is also super simple. Just use the method spark.read.parquet with the path of the Parquet file. After displaying its schema and content, we are sure it has been read successfully. And as always, it is recommended to stop the Spark session when finished the Spark tasks. That wraps up our journey through creating data frames from various data sources using PySpark. In today's video, we'll be diving into some essential data frame operations that will help you analyze your data effectively. Let's get started. In the first step, we need to set up our environment to work with Spark and create a Spark session as usual. Here we named our Spark session data frame operations. Next, let's load some data into a data frame. We'll use a synthetic dataset that represents product information. The data is stored in a CSV file called stocks.txt. Here, we use the spark.read.csv method to read the CSV file. We set header equals true to treat the first row as column headers, and infer schema equals true to infer the data types of columns. Let's explore the data we loaded. We'll print the schema and display the first 10 rows of the data frame. The print schema method shows the data types and structure of columns in the data frame. The show 10 method displays the first 10 rows of the data frame. Now, let's go through various data frame operations that you can perform in PySpark. Selecting columns. The select method allows you to choose specific columns. Here, we've selected the ID, name, and price columns. Filtering rows. You can use the filter method to apply conditions and filter rows. In this example, we're filtering rows where the quantity column is greater than 20. Grouping and aggregations. The group by method groups data based on specified columns, and the ag method allows you to perform aggregations like sum and average on group data. Joining data frames. The join operation allows us to combine multiple data frames based on specified columns. In this code, we create another data frame df2 with selected columns, and use the join method to combine the two data frames based on the ID column. The result is a new data frame called join_data, which only contains rows whose IDs are matched in both data frames. Sorting data. Next up, we'll learn how to sort rows based on one or more columns using the order by method. In this code, we sort the data frame df by the price column using the order by method. The data frame is now sorted by price ascendingly. We can also sort by multiple columns and in descending order using the desc function from the PySpark.SQL.Functions module. The result shows now it was first ordered by price descendingly and then by ID descendingly. When the price is the same, the row with a larger ID will be ordered first. Getting distinct rows. The distinct operation helps us find unique rows within a data frame. Here, we select the category column and use the distinct method to get unique product categories. Dropping columns. With the drop operation, we can remove specified columns from a data frame. Let's say we remove the quantity and category columns from the data frame using the drop method. Adding calculated columns. Using the withColumn method, we can add new calculated columns to a data frame. For example, we create a new column, revenue, by calculating the product of the quantity and price columns. Renaming columns. Lastly, we'll learn how to rename columns using the withColumn renamed method to improve column readability. In this example, we rename the price column to product_price using the withColumn renamed method. In the end, we need to stop the SparkSession as a best practice. Congratulations! You've just completed a comprehensive tutorial on PySpark data frame operations. In today's video, we'll explore the powerful world of Spark SQL and SQL operations with PySpark. Let's get started. Spark SQL is a Spark module that facilitates querying structured and semi-structured data using SQL commands. It extends Spark's capabilities to handle structured data and allows users to seamlessly switch between SQL queries and Spark's core APIs for data processing. Here are the key features of Spark SQL. Unified data processing. Spark SQL provides a unified API for both batch and real-time data processing, making it easier to build end-to-end data pipelines. Schema inference. It can automatically infer the schema of structured data sources, reducing the need for explicit schema definitions. Data source abstraction. Spark SQL supports a wide range of data sources, including Hive, Parquet, Avro, ORC, JSON, and JDBC, making it versatile for working with different data formats. Integration with Hive. It can seamlessly integrate with Apache Hive, allowing you to run Hive queries and access Hive UDFs within Spark SQL. Let's do a step-by-step demo on how to perform SQL-like queries on data frames in PySpark. First, initialize a Spark session. To get started, you need to initialize a Spark session, which is the entry point for using PySpark's SQL capabilities. Here's how you can create one with a proper app name like DataFrame SQL. Second, load data into a data frame. You can load data into a data frame from various sources like CSV, Parquet, JSON, or Hive tables. For this example, let's use a CSV file named persons.csv with a header and columns of name, age, gender, and salary. Third, register the data frame as a temporary view. To run SQL queries on the data frame, you need to register it as a temporary view. We can simply achieve that by using the method createOrReplaceTempView and giving it a name like my_table. Fourth, perform SQL-like queries. Now that you've registered the data frame as a temporary table, you can use SQL-like queries to analyze the data. For example, we can select all rows where age is greater than 25. Or computing the average salary by gender with SQL queries. To view the results of your SQL queries, you can use the show method. Creating and managing temporary views. In PySpark, you can create and manage temporary views to work with data frames using SQL-like syntax. Like what we already did, to create a temporary view from a data frame, you can use the createOrReplaceTempView method. This method registers the data frame as a temporary table that you can query using SQL-like syntax. For example, we can create another temporary view named people. Once you have created a temporary view, you can query it using SQL-like syntax with the spark.sql method. For example, getting all the rows with age more than 25 by querying the temporary view. You can check if a temporary view exists using the spark.catalog.tableExists method. This can be useful before attempting to create or query a temporary view. Lastly, dropping a temporary view. To remove a temporary view when you're done with it, you can use the spark.catalog.dropTemp method. This frees up resources and removes the view or table from the catalog. Using advanced SQL operations for data analysis. In PySpark, you can leverage advanced SQL operations to perform complex data analysis on data frames using SQL-like syntax. These advanced SQL operations can help you gain insights, perform transformations, and solve more intricate data manipulation tasks. Here are some examples of advanced SQL operations in PySpark. First, subqueries. Subqueries are nested SQL queries that can be used within another query. You can use subqueries to filter or aggregate data based on conditions from another table or subquery. Here we create two data frames called employees with ID and name, then salaries with department, ID, and salary. Let's register them as temporary views. Then we can use subquery to find employees with salaries above average. Here, we use the query to get the average salary in the salaries table. Then use it as a subquery to select the ID of the employees whose salary is above the average. Then use the whole query as the subquery to get the employee name from the employee table. Second, window functions. Window functions allow you to perform calculations across a window of rows defined by an ordered partition of the data. Common window functions include row_number, rank, dens_rank, sum, avg, and more. In this example, we will calculate the rank of employees within each department based on salary. Let's first join the table employees and salaries to have a data frame called employee_salary with columns department, employee ID, and salary. Then we create a window specification of partition by department and order by salary descending. Then we create a rank column to rank based on the window's specification. From the result, we can see the rank of the employee's salary within each department by salary. These are just a few examples of advanced SQL operations you can perform in PySpark. In the end, we need to stop the SparkSession as a best practice. Congratulations! You've just completed this fantastic PySpark tutorial, and I couldn't be prouder of your dedication to learning. Before we wrap up, I'd like to remind you to hit that subscribe button and give this video a thumbs up if you found it helpful. And here's the real kicker: sharing this video with your friends, colleagues, and fellow learners to unlock the exciting practical end-to-end bonus video about Spark machine learning and Spark streaming. Thanks for watching, and see you in the next video.